So we're going to hear more from Janet. So now that we've all learned about F-singularities, she's going to tell us about extremal hypersurfaces in positive characters.
Great. Thanks so much. Great. So we're going to start with the following setup. So K will be a field of characteristic P. I'm often going to assume algebraically closed. I will try to tell you exactly when I need it in general. Okay, R is our polynomial ring. And M is going to be our homogeneous maximal ideal. All right, and I want to pick a homogeneous and reduced polynomial of degree D. For some D. I'm just labeling the degree. And maybe note that's out. A projective variety, so I can think about, I'm going to denote it this way. So and then I also want to think about its affine cone. So, and its affine cone, maybe I should write, maybe denote the C of X. All right, so if I just think about the points in K to the n plus 1 and affine n plus 1 space, where this is. Okay. Okay, what we're going to study is the F-period threshold of S. That's a homogeneous maximal ideal. Okay, and what I want to say about it, a lot of you, probably most of you were here this morning, so I won't repeat everything I said. I'll just say a tiny bit about it, just to remind you. Maybe note, in general, this is some invariant that varies between 0 and 1. And being 1 means that you're either smooth at the point M, or, and maybe I'll say, I'll draw a picture and say explicitly, or you have mild singularities. So this kind of means mild singularities, depending on who you ask, what their conditions. And then this can be worse. As I get closer to 0, worse singularities. And maybe explicitly what I'm saying is that, let's think of this cone. So I've got some projective variety, I've got some affine cone over it. And if I'm studying the F-period threshold at this homogeneous maximal ideal, what I'm doing is I'm studying this cone point. Singularity. So there's our general setup. And this story really starts, well, the story of what I'm going to call extremal hypersurfaces, which I'll tell you what they mean in a few minutes, really starts with the following theorem. All right, so I have the following theorem. And this started at a workshop in Banff, so we have a lot of co-authors. We'll probably start abbreviating it, right? So this is joint work with Javek Kostrizova, Jenny Frankel, myself, Jyoti Singh, Karen Smith, Adela Maracchio, and Emily Witt. And this is from 2022. And what we showed is that, so K is character P, happens in this guy, and this is going to be reduced and homogeneous. Then what we did is we gave a lower bound on the FK threshold, and then we also actually showed that it was sharp and explicitly can tell you exactly when that lower bound is sharp. So I should say degree E. Then the FK threshold at this point F is always greater than or equal to 1 over D minus 1. Okay, so it's got some lower bound in terms of the degree. And then we can classify exactly when it hits this lower bound. So when it hits this lower bound should be sort of our worst singularities as measured by this invariant. So it should be sort of the worst cone point. So with equality, if and only if F is contained in its maximal ideal to the PDE. So this is E, some of the PDE. And I should say for some E, well, we're going to write the end first, and D is equal to P of D. So maybe this theorem statement gives us a natural definition. So we'll say V of F, so this projective hypersurface. I might misspeak and call both the projective hypersurface and the affine hypersurface extremal, but this is what we do in our paper. So we'll say this hypersurface is an extremal hypersurface. If it achieves this lower bound. Okay, so in other words, if its affine cone has this most singular possible cone point, as measured by this invariant called the F-ray threshold. Okay, so maybe let's unwrap our theorem a little bit and talk about which polynomials can show up. So and yeah, you might object, this word extremal, it's only extremal with respect to this one invariant. Hopefully by the end of the talk, I'll convince you that this is actually a good name. They show up, they have other extremal properties, which we'll talk about. Okay, but let's just unwrap this definition. Not definition, this theorem. So we said we hit this equality only if I'm contained in this maximal ideal to the P to the E, and my degree is P to the E plus 1. So so F has to be m to the P to the E, and the degree of F is P to the E plus 1. Okay. In other words, I could write F in the following way. So it's got to have it's gotta have terms like this, where these are, I mean, some of these could be zero, but these are just linear forms in their variables. Right. All right, maybe another note. You want to switch it?
Oh, yeah.
In other words, we could think about, sorry. Oh, yeah, I know, I put a secret board.
Oh no,
underneath.
oh, it's in school.
It's okay, I'll use this one, then I'll not move. I see, okay, I should do.
I mean, every board gets erased at some point, so nothing will be.
Okay, yeah, sure, I'll do the hot board first.
Sorry.
No, it's fine. In other words. We could write up in the following form. Oh, sorry, no, okay, so what do we do this? So I'm gonna take an n by n, oops, no. So I changed my notation so that I can talk about projective space and say n, but this is now n plus one. By n plus one. Coefficient matrix. And previous. Okay. And so in other words, my rows just correspond to my coefficients of my linear forms. Okay. Hi. Here's the coefficients. Okay. And maybe you might ask, if we're kind of concerned with the projective variety these guys define, maybe you only care about these up to a linear change of variables, because that won't change the geometry of our projective hypersurface. So what are these up to linear changes of variables? So we have a theorem. This is in the same paper. This paper is called Lower Bounds on the Upper Threshold of Extremal Singularities. So, if we have that is extremal, then after a linear change of variables, assume. Right, so we can always write them in this form with this matrix. So we can assume something about the matrix A. So A is block diagonal. And you can put the blocks in any order you want just by swapping variables. So let's say non-decreasing block size. Where the blocks are, all right, so they're either just one, for size one, or They're just a matrix with ones on the upper diagonal and zeros everywhere else. Great. So maybe as a corollary of this theorem, you can just count these. So I guess in my notation as I've done it, there's n+1 variables. The number of extremal hypersurface up to, let's say, a fixed degree d equals p to the plus 1. Yeah, and notice this, like, this works for every choice of e. So for every choice of e, this is a very subtracted swing. So the number of extremal hypersurfaces of degree d equals p plus 1 in, maybe I'll say in n variables, is we just choose the block sizes in our matrix, our n matrix. So it's just the number of partitions. Oh, and I should say, I want to say non-degenerate. So there are more if you're counting the ones that could be written in a smaller number of variables. But if you want all of them, you just sum this all up. So non-degenerate. Meaning I'm writing down. Plus. Okay. So here's our classification. Yeah, maybe I should manage the words better, but I want to give you an example, and I didn't want to spend a lot of time writing it out. So let's say the example in the case that we have 4 variables. So in the case that we define a projected surface.
What do you mean? It's a hypersurface. How do I have to write this down?
So for example, like if there's a linear change of variables, that sends it to a fewer number of variables. So in other words, like.
But the dimensions. Okay,
Like let's just. I mean, this is not reduced, but here's a simple example. Right, there is a linear change of variables that sends that to x. So that's not that's not what I mean by non-degenerate. Maybe I should put like a plus. Maybe I should make this reduce. But there's a linear change of variables. I got sending x plus y plus z to x, and 7 will be intended y. And then this I can write this in two number variables. So this is an example of something that's not non-degenerate.
Yeah.
Well, it's not living. It's a hypersurface. It was living in a plane. Would be that type of plane.
Sure, so we don't want to include the hyper.
No, this is this is a different notion. That's why I was confused.
Yeah, I guess.
I know.
I mean, algebraically non-degenerate. I don't know. If you people object to the word non-degenerate, but yeah, exactly. This is exactly what I mean. It's just that there is no linear change of variables that sends you to some smaller number of variables. Great. So if you want all of them, you can count up. Yeah, just summing up all of them. Okay. Great. So I want to give you an example of this. So if I think about, these are all the extremal surfaces up to equivalence are defined by these equations. So in other words, I'm picking half K W. Oh, and actually, I see. I should say this theorem. Okay, this change of variables does require algebraic cluster. It probably requires slightly less than that. But it definitely works over the algebraic closure. Otherwise, you can have more of these things. But I don't want to say, yeah, so this is going to be over an algebraic closed field. Is what I can assume now of this one. All right, so here's the example. So here are all of the extremal surfaces of the projectile equivalence. So I can have sort of the Fermat degree q to the plus 1, so x to the q to the plus 1 plus y to the q to the plus 1 plus c to the q to the plus 1 plus w to the q to the plus 1. That corresponds to just choosing all my blocks to be size 1. And then I could choose, 2 blocks of size 1 and 1 of size 2. I get this form. I could choose a block of size 1 and a block of size 3. I get this guy. So
Can I see again the given?
yeah, sorry.
So you said that like the blocks, the K blocks as one on the diagonals?
One's on the upper diagonal. So it's zeros on the diagonal.
Oh, okay.
Yeah, it looks like a door performance.
Okay, now it's clear.
Yeah, one's on the upper diagonal and zeros elsewhere.
So in particular, this is independent of what the characteristic is.
Yes.
They're all extremal and they all have the same F pure threshold.
Yes. But you'll notice that like only these special degrees show up. But it works for every E. So for every fixed E, there are this many equivalence classes of these extremal types. Great. So I can also, I can use one block of size 1, one block of size 3, or 2 blocks of size 2, or just a block of size 4. And maybe I'll note that, so again, all of these at the affine cone point, of course, are singular, since they're cone points. But this one is smooth as a projective hypersurface, or projective surface. So it's the only one whose affine cone has an isolated singularity at the cone point. The other ones, most of them are normal, except for this one. So these ones are normal. And then this one has a singular locus. It's singular along. Okay. Great. So for the rest of the talk, I want to kind of, not completely switch gears, but I want to switch gears to kind of focus in on this surface case, because I sort of want to understand extremal hypersurfaces in general. We're going to start by studying extremal surfaces.
So,
And maybe, sorry, go ahead.
so super naively, I'm seeing that more ones in your matrix seems to make something nicer, and fewer ones in your matrix.
Oh,
seems to make
you can
something
read, you can read the singularity locus off of, it's the one, it's n minus the rank of the matrix. Yeah. So, yeah, you can just directly compute the singular locus. Yeah, so like as an example of, well, maybe I won't say. Yeah, there are like degenerate guys, but I guess the point is that I can write them with rows of zeros at the bottom, after some change.
It's
So, yeah.
also not normal. It's 3.
Not that affine cones. They're singular at a point. They're singular at the origin, at the cone point, and at another point.
If they could be singular and still normal, but they are not.
The affine cones now, yeah. I think that's okay, yeah, for the rest of the talk, I want to kind of shift gears and think about projective surfaces in general, kind of to explicitly understand this case. And as a starting point, we're going to focus just on this one. So we're going to focus on smooth projective surfaces. Because we have a kind of extensive theory of smooth projective surfaces in general, then we can say lots of interesting things in that case. All right, so how can we study smooth projective surfaces? All right, I'll give you a really like classical answer. Is do they have lines? And if they do, how many? All right. This might be one way you want to study them. All right, and then maybe I'll note this highly depends on our degree. Right? So, right, if it's just kind of a warm-up, if D is 1, not so interesting, we have infinitely many lines, even through every point. And when D is 2, we also have infinitely many lines. We have a smooth quadric surface, and they kind of come in two families. So for every point, there's exactly 2 lines, but in general, there's many 2 rulings. All right, and then for D equals 3, I'm not going to draw a cubic surface, but maybe most of you know what we get 27 lines. Yeah, I should say K equals K bar here, otherwise some of our lines can disappear. All right, and then what happens for higher degrees? Generally, we don't have any lines, but we can have lines. For D bigger than or equal to 4, often no lines. But there are bounds in terms of degree. Yeah, if I remove smooth, this is where you could still have infinitely many lines. Like even like for example, a cone obviously has infinity lines. But yeah, bounds. Three. Yeah, when I think this is classical, I do mean really classical. So the first result that I know of at least is Klepsch from 1861, which says when K is characteristic 0, there are less, and I take a smooth projective surface, then there are less than or equal to D times D minus 24 lines on any smooth surface of degree D. The next result comes about 80 years later. And I should say, there was actually a small problem in this paper. It is still true. But there's at most, again, this is K characteristic 0. This is actually a smaller lower bound, or smaller upper bound, D minus 3 times 11D minus 6. And I should say these are, I guess these are all for D bigger than or equal to 3. When you plug in 3, you should get 27 for all of these. All right, and then the next. No,
Like if E is 3, then I get.
Then you get-
0 for the next one.
oh yeah, sorry, this one is this wrong? Maybe this is the wrong. No, I think it's d minus 2 times 11 d minus 6.
So we can see if we get 27.
Yeah, check if you get 27 if I do this.
D minus 2.
D minus 2 it is. Yeah, maybe I wrote something down wrong. So maybe I should double check. Well, it doesn't matter. The last one I think will definitely be right. I multiplied it out. So, yeah, great. So the next result comes like another 80 years later, roughly. Oh, not exactly. This is due to Bauer and Roms from 2023. All right, and finally we break into characteristic P, but only for some characteristics. So for K characteristic 0, or K characteristic P, but it has to be bigger than the degree, which in our extremal surfaces we never are, because our smallest degree is P plus 1. Okay, but they do say that the number of lines is bounded by 11d squared minus 30d plus 18. And again, I hope if I've written this down right, it should give you 27 if you plug in 3.
Atomic 11d squared, that's kind of.
It's not sharp. So I think like maybe 70, I don't know, maybe I shouldn't conjecture, but I think maybe 70 squared is the right asymptotic for characteristic 0. But I'll tell you exactly what it is in characteristic P. But yeah, it's interesting that they're all kind of 11d squared, but that's not at all. None of these are sharp, even for d equals 4.
Okay, so these are all bounds for the same thing. They're just getting.
Yeah, they're just getting better. So they're all bound to the same thing. These are all number of lines.
Every 80.
Every 80 years we get a bound. So in 80 years, these are all the number of lines on X, a smooth surface of degree d.
That's way.
All right, so let's see examples. So this is going to be an example of why these aren't sharp. So when d equals 4, the smallest of these bounds is the last one, even at d equals 4. So 11d squared minus 30d plus 18. Hopefully, if I've written this down right, is 74. But it's known, I think it is right. So remember, this is the bound for characteristic 0.
Okay.
Or characteristic P bigger than 4. All right. However, there are actually less than or equal to. All right, so the real bound in the case of theorem folds is 34. And maybe I'll say these are attained. So there's at most 64 lines when K has characteristic 0 or characteristic P bigger than, starting at 5. Okay, and then we only have two other characteristics to think about, so we might as well. And actually, that's where this theorem breaks. So there's actually 112 lines, and again, this is attained. When K is characteristic P equals 3. And then you can do characteristic 2 as well. They're actually, the bound does work in characteristic 2 in this case. There's actually less than or equal to 60 lines. Characteristic 2. Great, and I think this is the characteristic 0 case here. This is due to Segre. This is due to ROMs and shoot. I think 2015. Maybe I won't put it because I don't remember. I think this is in that 43 paper. Oh yeah, they are. You can produce a surface over a field of characteristic 2 which has 60 lines. Yeah, K is K bar. So you're only, if you don't assume K is K bar, you could possibly lose lines. Yeah. So I don't know the statements off the top of my head when you don't have an algebraically closed field. Right, like if you have some lines in over some field, you still have them over the algebraic closure, but you possibly have less that you've lost. Okay. Sorry, go ahead.
Should have.
Oh yeah, it does. Maybe one last example. I'll give this example. Maybe this example is yeah. Over a field of characteristic 3. Here. Our other example is just the generalization of this example. So characteristic B, if B is e to the B plus 1 for some B, then our smooth extremal surface has way more lines. It has b squared times, but we're going to do the fourth. B squared minus 3b plus 3. All right, and then actually this is our theorem that not only does it have these way more lines, actually this is the most lines you can possibly obtain. All right. This is joint work with this is myself, Tim Ryan, and Karen Smith. And this is on the archive, so it's not published. So I guess we put it on the archive. So let X be a smooth projective surface over. I'm going to tell you why I need algebraic closure. There's two parts to the theorem. The upper bound will hold regardless of algebraic closure. So let X be a smooth projective surface over a field, algebraic closed field of characteristics P. Then the number of lines on X is less than or equal to this number. With equality, if and only if X is a smooth extremal surface. i.e. Let's just look at because of averaging. Great. So there's our statement. Maybe in the last, maybe I should say, one thing, this is work in this paper, but maybe I should also mention that we also wrote a paper, the same co-authors, but also with Anna Prosowski. These ideas. And those authors. Plus, so we wrote another paper sort of about the configurations of lines on, well, the geometry in general. Okay, maybe in the last 5 minutes, I'll tell you just a little bit about this proof.
Janet, we stole like 3 minutes from you dealing with the tech setup also, so you
Okay.
have the 3 minutes.
Okay, cool. Okay. So, in order to get the upper bound, maybe I'll just say something about, the classification in a second. By the way, hopefully this convinces you that maybe our word extremal is okay, at least in the case where we look at the smooth extremal surface given by an extremal hypersurface. It has the most lines possible of any smooth surface. So it's at least extremal with respect to tangential lines. All right, so for the upper bound, we first found what's called the Picard number. Okay, so what you can think of this as is if I think about, one way to do it is if I think about all possible divisors and I mod out by numeric equivalence, so I think about how they intersect with other curves, then if I take the rank of that, say the second Picard number, so he just with our characteristic. Oh, sorry, let's say, yeah, I want to change, I'll keep X as my surface. The reason I wanted to change to S is so I didn't have to write with a characteristic. Maybe I just won't make it simple. Okay. And this part of the proof is like entirely just using other results. You have to be a little bit careful about what you mean characteristic P, but this is sort of known things. And then what we want to do is we want to find a bunch of divisors that are numerically independent. And so we want to play that off of this bound to say, like sort of an upper bound for some classical. So we fix a line L on our surface, our smooth surface, and use this to bound the number of lines intersecting it on X. Okay, this proof is just explicitly finding a bunch of lines plus a hyperplane class that are numerically independent. So maybe what I'll say, I've got like 3 minutes. Okay, so explicitly, I can tell you exactly the ones we pick. So we look at our line L, and we consider all hyperplanes that contain L and contain other lines of our surface. Look at all of these guys. And there's finitely many of them. You can show this using this bound 1. If there weren't, you end up getting, you can break the bound 1 hard, right? And then what we do is we look at, so we pick, either we take all of the lines except for L, or if there's D lines on one of these hyperplanes, we also delete one more. And it turns out that that set of lines, so all of the lines on all these hyperplanes, either minus L or minus 1, plus L plus a hyperplane class is numerically independent. So maybe I won't write it. But anyway, so find set of lines. And then play it off of this card rank.
So it's like,
Yeah, the surface isn't V3. Yeah, maybe I should say, that's kind of based on the fact that I've written it. Oh, I didn't write it, maybe. Yeah, I should write it. I guess before I was kind of fixing a polynomial and saying my x by BW, this is living inside of the space. Yeah, exactly. And maybe a corollary of our fact.
All of the bounds are also V3, right? Like stuff. This is
Sorry.
all the bounds are also. To these.
Oh yeah, all of these guys are V3. Yeah, these are all about smooth surfaces in V3. Yeah. Okay, so a corollary of 2 is that X has the most possible lines intersecting L is fixed. So you kind of play 1 and 2 off of each other, but we end up getting that we have the most possible lines intersecting L if and only if L lies in, I think d squared minus 2d plus 2 planes, each containing d lines. So yeah, just as an observation, X is degree D, so the most lines we could have in any plane is D lines. Okay, and then the last step is to bound the number of lines on X skewed L. And I was gonna write out more of this proof, but maybe all I'll say about this proof is actually completely algebraic. All it really uses is Bézier's theorem. So it has to do with sort of if there aren't any skew lines to L, you're kind of done. If there are, sort of choose how to represent them and then kind of play with what you know about your equation. So this is an algebraic. Okay, and then maybe I won't say too much about the classification. The classification actually, I'll say a couple things. The classification actually uses some results about from finite geometry about the potential configuration of lines And it finds an explicit configuration of lines and then does something algebraic with it to say, actually, up to projectile equivalence, we can say exactly what this, what these surfaces look like. Okay, so maybe I'll stop.
Cool. What questions are there for Ken?
I'm curious, I guess, about the order of discovery of this. Like, when you found these extremal surfaces, did you discover that they had this many lines that tried to move bound, or did you found and then find that these surfaces had that many lines? Or
Yeah, so we knew they had that many lines. That's actually that is actually known before. So I think maybe the person, and maybe I don't want to say, these lines form like sort of a classical incidence structure called a Hermitian generalized quadrangle, and it was kind of known exactly how many lines there were. So we knew how many lines it had. We knew that this is an example of something that breaks. Maybe this wasn't observed, so I think it was observed by Kolar in one of his papers, but it should have been known that this number of lines breaks the characteristic zero bounds for numbers of lines. But yeah, we felt that, so we knew it had this many lines, and we felt that that should be the most possible lines. And we felt that these things really should be sort of the worst case scenario in this respect. Yeah, good question.
I have one. So I'm wondering, so you justified why the first guy is extremal in at least two different senses of the word.
Yes.
Do you think that there should be, and like counting lines on something singular is kind of a different deal, but do you think there should be something similar to your line counting that should make the other guys like extremal in their singularity class or something like that?
Yeah, so we have, maybe we should publish it. We have some notes on the lines on the other guys. So unfortunately, there can be actually like a pretty small number of, there's one of them that has infinitely many lines. But then the other ones can actually have like a pretty small number of lines, like I can't remember, maybe like 2 or 4. I don't know. I think we have to like investigate more whether or not like lines is the right thing to think. I think they should be extremal in some sense, but I don't know if lines is the right thing. Possibly with multiplicity, they have like maybe the most lines, but yeah, if you actually just count like explicit lines, there can be small numbers of lines on those guys. But yeah, I don't know exactly what the right extremal property is for the other surfaces. And yeah, I expect, I mean, there's certainly, we've only really investigated the surface case. I expect there to be similar results about linear spaces on the higher dimensional ones, at least for the one smooth projective hypersurface. But we don't know yet. So yeah.
Extreme example, how did
How many -2 curves are on the extreme? I don't know off the top of my head. I don't know. There might be. I would need to think about it.
it has to be smart. It has to be smart. Some lines there.
Yeah. Yeah, so I don't know off the top of my head. Yeah, I haven't thought about it, but maybe there's something you could say. Yeah, for a while we were thinking, so we have a paper, that big group of co-authors called Cubic Surfaces and Characteristic 2. And for a while we were thinking extremal surfaces should sort of generalize cubic surfaces, and in some ways they kind of do. And in the cubic surface case, you can think of this as P2 blown up at 6 points, and you can kind of say something explicit about what happens to those blowups. So yeah, I don't know. But yeah, I'm not in the general, yeah, I don't know. Anyway, so I don't know the answer to your question. I have to think about it. But for a while we were thinking that maybe this is like some blowups. It's not. It's not just like an explicit generalization of cubic surfaces in that way. But I don't know.
Any questions on Zoom? Oh yeah, Janet, can you check the chat?
Thanks, Janet. No, I think. No questions.
Okay, let's thank Janet again for those.